Welcome to the Explainer. Today we're going to tackle one of the most powerful and, for the longest time, one of the most controversial ideas in all of physics, renormalization.
Okay, so let's just dive right in. Imagine you have what you think is the most precise theory ever devised about how light and matter work together. But every single time you use it to calculate something really basic, the answer comes out as infinity. Well, that was the actual crisis facing physics back in the 1940s, and figuring it out is one of the greatest intellectual detective stories in all of 20th century science.
So this whole saga kicks off with a theory called quantum electrodynamics, or QED for short. Now, this was supposed to be it, right? The ultimate description of the electromagnetic world. But it had a very big, very infinite problem.
And you really have to stop and appreciate just how absurd this problem was. Physicists were trying to calculate the most fundamental properties of a single electron, its mass, its charge, and their best, most beautiful equations just kept spitting out infinity. I don't mean a huge number, I mean literally infinity. This wasn't some minor rounding error. It meant the theory, for all intents and purposes, was completely and utterly broken.
The source of all this infinite madness comes from the truly bizarre nature of the quantum world. You see, in the quantum world, an electron is never truly alone. It's surrounded by this fizzing soup of virtual particles that just blink in and out of existence all the time. The electron is constantly interacting with this personal little cloud. And when physicists tried to add up the effects of every single one of those tiny interactions, the sum didn't just get big, it just exploded. It went to infinity.
So these pesky infinities had a technical name: ultraviolet divergences. And that's because they were popping up from these virtual particles with just insane amounts of energy. The bottom line? It meant that QED, for all its beauty and elegance, couldn't make a single useful prediction. It was, useless.
So, faced with this complete theoretical disaster, a whole generation of brilliant physicists, we're talking Feynman, Schwinger, Tominaga, they developed this set of techniques that were honestly both outrageously successful and really unsettling. They basically figured out a way to tame the infinite beast.
The solution they came up with was kind of like this three-step dance to basically sweep all those infinities under the rug. First, they'd put in a temporary limit. They called it a cutoff, just to stop the math from completely blowing up in their faces. Then, and this is the really clever part, they would absorb all that infinite garbage into the bare mass and charge that were already sitting in the equations. And what was left over? A nice, clean, finite number. Something that gave them predictions they could actually go out and measure.
So here's the absolute core idea, right? The mass in charge that are just written down in the original equations, those are the bare values. And they basically said, you know what? We can't actually measure those. They're just theoretical placeholders. The only thing that actually matters is the renormalized value. That's the mass in charge we measure in a lab, which, by the way, already includes all those messy self-interaction effects. So by cleverly subtracting one infinity from another, they were left with these perfectly finite answers. And the crazy part? They matched experiments with just jaw-dropping accuracy.
But here's the kicker. Even the guys who invented this whole thing thought it was kind of sketchy. Richard Feynman, one of the main architects, he literally called it a dippy process and hocus pocus. It just felt like a cheap mathematical trick, like hiding a mess in the closet because you don't know how to clean it up.
And the legendary physicist Paul Dirac? Oh, he was even more scathing. He basically said, this isn't real math. Sensible math is when you ignore something because it's tiny, not because it's infinitely huge and you just don't like it. And for decades, this was the central puzzle of renormalization. It worked. It worked perfectly, but nobody, and I mean nobody, had a clue why this mathematical shell game was actually describing reality.
So that mystery, why on earth does this dippy process actually work? It just hung over physics for decades. And then in the 1970s, a physicist named Kenneth Wilson comes along and has this incredible insight that just changes, everything.
Wilson's revelation was a total game changer, a complete paradigm shift. He basically said, hey everyone, renormalization isn't a bug. It's not a mistake we need to hide, it's a feature. That whole trick was actually revealing a fundamental truth about how the universe works.
What he realized was that the laws of physics aren't set in stone. They depend on the scale you're looking at. This gave us the idea of running couplings. What does that mean? It means the strength of a force, like electromagnetism, isn't just one single number. Nope, it actually changes depending on the energy of the particles that are interacting.
Those infinities that played the old QED calculations, they were just a symptom of a really naive assumption that a single value for an electron's charge would work at every single energy scale in the universe.
And this is where it gets really cool. For QED, the electromagnetic force actually gets stronger the closer you look, at higher energies. But for quantum chromodynamics, that's the theory of the strong nuclear force that holds quarks together inside protons and neutrons, the exact opposite happens. The strong force gets weaker at higher energies. This whole phenomenon, they called it asymptotic freedom, and it was a direct prediction of this new way of thinking. It was so huge it won a Nobel Prize.
So, with Wilson's brilliant insights, renormalization was totally transformed. It went from being this suspicious, slightly embarrassing mathematical trick into one of the most powerful and profound conceptual tools in all of modern physics.
It gave us this amazing framework called effective theories. Think of it this way. We can now build incredibly accurate theories for the world at a specific energy scale, like the world of atoms and chemistry, without needing to know the ultimate final theory of everything that might describe quantum gravity. It lets us do physics in layers, like a stack of maps, where each map is perfectly good for its own territory.
And the impact of this idea, it is just staggering. This isn't some obscure little concept. It is absolutely everywhere. It is the very foundation of the standard model of particle physics. It explains this wild thing called universality, why completely different systems like water boiling and a magnet losing its magnetism behave in mathematically identical ways. It's a crucial tool in condensed matter physics, and it's the basis for how physicists try to build grand unified theories, or GUTs, to unite all the forces of nature.
Okay, so after all that, what are the big takeaways? What should you remember? First, the laws of nature, as we see them, are not absolute. They're scale-dependent. Second, we can do absolutely incredible, precise science without knowing the ultimate theory of everything. Third, sometimes wildly different things in the universe share deep hidden connections. And, maybe most importantly, sometimes the biggest, most frustrating problems, like getting infinity as an answer over and over again, are actually pointing the way to a much deeper, more beautiful understanding of reality.
You know, renormalization began its life as this desperate trick, a way to deal with an impossible infinite problem. But it ended up giving us a completely new philosophy for how to understand the universe, one layer at a time. And it leaves us with this incredible, tantalizing question. If our physical laws are just effective descriptions for a given scale, are we just peeling back the layers of a truly infinite onion? Or is there, at the very bottom, one final, fundamental law of nature waiting to be found? And that's the question that continues to drive physics forward today.